So far, the infinite series that we know about are extremely limited in nature. We know about geometric series. We've discovered that the harmonic series doesn't converge. We know a little bit about telescoping series, but that's all. In this discussion, I want to talk about a convergence test that is less direct than the others, and this is going to be called the integral test. So let's set this up. The premise is that I have some ordinary function f of x. This function is positive, continuous, and decreasing on the interval from 1 to infinity. And in addition, if I were to insert positive whole numbers in for the x, I get the terms of an infinite series that I'm interested in. If all of these statements are true, then we can say something. We'll make the statement first and then look at why it's true. If all of these statements are true, then the sum equal 1 to infinity of ai and the integral 1 to infinity f of x dx either both converge or both diverge. So if I know about one of them, I automatically know about the other. If any of these hypotheses are not true, then all bets are off. It isn't very difficult to see why this is true. I need to make some inequalities. Firstly, I'm going to think about the area under the curve from x equal 1 to x equal 2. The function being positive is important here so that I can write the area as an integral of the function. When I put positive whole numbers into the f function, the resulting function values are going to be terms of the series that we're interested in, though. The region under the curve from x equal 1 to x equal 2 is contained within a rectangle that starts at x equal 1, ends at x equals 2, and has height a number 1. The width across the bottom is 1 unit. 1 times a1 is a1. The area of the rectangle outlined in red is a1 times 1. It contains the region under the curve, so the area under the curve must be less than or equal to a1. On the other hand, you can repeat this argument again. The area under the curve is the integral from 2 to 3 f of x dx. This is no more than the area of this rectangle, which is 1 unit across this way and a number 2 units in the up and down direction. The integral from 2 to 3 f of x dx is no more than a2. Repeating, the integral from 3 to 4 f of x dx is no more than a number 3. The integral from 4 to 5 f of x dx is no more than a 4, and it should be clear as to the pattern that's developing. The integral from someplace to someplace plus 1 f of x dx is no bigger than a number, the lower index. On the other hand, the integral from 1 to 2 f of x dx is the area under the curve from 1 to 2, and that area is larger than the area of this green rectangle, 1 unit across the bottom, a number 2 in the up and down. The area under the curve from 2 to 3 is larger than the area of that rectangle. This is 1 unit across and a number 3 in the vertical direction. Likewise, a number 4 is smaller than the area from 3 to 4. And the area of this green rectangle, which will be a number 5, is less than or equal to the area under the curve from 4 to 5. If I were to add all of these integrals, it would be the area under the curve plus that one, plus that one, plus that one. It would be the integral from 1 to 5, f of x dx. If I were to add these numbers, I would get a1 plus a2 plus a3 plus a4. If I add these, a2, a3, a4, and a5, if you were to continue this process until you were integrating from n minus 1 to n f of x dx, this will be bounded by two numbers, 5, 5, 4, 4, 3, 3, 2, 2, a number n, 1, 1, 2, 2, 3, 3, 4, 4, n minus 1, n minus 1. What I'm going to do is to add all of these inequalities together and then get something that I can relate to both the partial sums and what I might call the partial integrals of the improper integral. The sum on the right is partial sum number n minus 1 of my infinite series. The quantity on the far left is almost a partial sum. If it had a1 added in, it would be partial sum number n. So I'll express it that way. Suppose that the infinite series converges to some finite number, capital S. So as I allow the index to become indefinitely large, I get numbers that more and more strongly resemble S. Since all of the A numbers are positive, because the F function is, as I add terms in these partial sums, the partial sums become bigger. So it must be true that each partial sum is less than S. Also, since the function f is positive, its integral is positive. So I know all of these integrals, integral 1 up to n f of x dx, forms a collection of numbers which is bounded. Each of these integrals is between 0 and capital S. Not only that, because the function is positive, if you were to look at the integral from 1 to n plus 1 f of x dx. This would be the integral from 1 to n f of x dx plus the integral from n to n plus 1 f of x dx. Because the function is positive, this must be positive, and the n plus first integral is bigger than the nth integral. This means that the collection of these integrals that I'm looking at forms a bounded increasing sequence of numbers. Therefore, the sequence of integrals converges. If the infinite series converges, then the integral from 1 to infinity, f of x dx, converges. Under the hypothesis that we've stated, if the infinite series converges, then the integral converges. If you take math reasoning, you'll learn about symbolic and manipulative logic. It turns out that this statement, if the first thing, then the second thing, is logically equivalent to if the second thing is not true, then the first thing is not true. This is called the logical contrapositive of that statement. So, given that we've figured out this first sentence, we get a second sentence for free. So far, we have two situations in which the series and the integral have the same behavior as far as converging or diverging. Looking at it, though, it's incomplete. I don't have a sentence, for instance, that starts off with, if the infinite series diverges, then something happens. And I don't have a statement that starts off with, if the integral converges, then something happens. So we will return to our double inequality and see what we can figure out. Suppose that the infinite series diverges. Then I claim it must be true that the partial sums become indefinitely big as the index increases. If that were not so, I would have a bounded set of partial sums, but on the other hand, I obtain a partial sum by adding a positive number to the previous one. That would make a bounded increasing set of partial sums, which would say that the infinite series converges, which contradicts the statement that it diverges to start with. So if the infinite series diverges, it must, in bad language, equal plus infinity, which means that by making the index big enough, you can make the partial sum as large as you care to make it. However, the integral from 1 to n f of x dx is at least as big as one of these partial sums minus a constant. Since the partial sums become indefinitely big, that means these integrals have to become indefinitely big as well, and so they diverge then. If the infinite series diverges, then the integral diverges. And then again, by logical manipulation, if this is not true, then that is not true. If the integral from 1 to infinity f of x dx converges, then the sum I equal 1 to infinity ai fails to diverge, and now we see that the integral test is valid. If the series converges, so does the integral. If the series diverges, so does the integral. If the integral diverges, so does the series. And if the series converges, this is the first one we did, then the integral converges. So, under the assumptions of the integral test, the convergence or divergence behavior of the sum and the integral are the same. It's a yes no type of thing. If I know one of them converges, I know the other one does. If I know one of them diverges, then so does the other one. As an example of this, let's look at the sum n equal 1 to infinity, 1 over n squared plus 1. When n is 1, the term that you're going to have will just be 1 over 1 squared plus 1. S number 1 is 1 half. S number 2 will have, in addition, 1 over 2 squared plus 1, 1/5. S number 3 will have 1 over 3 squared plus 1, 1/10, and so on and so forth. What I'd like to think about is whether this collection of partial sums, what I get as I continue adding more terms on, do these partial sums approach a certain number or not? We'll use the integral test to decide this. We'll create a function f of x equal 1 over x squared plus 1. Firstly, if I put only whole numbers in for the x, I reproduce the terms of my infinite series. Secondly, obviously f of x is always positive. F of x is always continuous since it's a rational function, and there's no real x value that makes the denominator 0. And I believe it's pretty clear that as you make the x bigger than 1, and then larger than that, 1 over x squared plus 1 gets smaller. So f is positive, continuous, and decreasing on the interval from 1 to infinity, just as we want it to be. Having checked that the setup for the integral test is okay, I need to look at this improper integral. If that integral converges, it tells me that my infinite series converges as well, and if the integral diverges, then the series diverges. I have to keep in mind there is no such number as infinity. I can't take an antiderivative and stick infinity and 1 into it and subtract. That doesn't make very good sense. Instead, I'm going to integrate from 1 up to some finite value of b and get an answer. That answer will have b in it, and then I'll take the limit as b tends to infinity. This is, you'll recall, the definition for this symbol, so this is what I have to do if I want to be careful. An antiderivative for 1 over x squared plus 1 is arctan x. I'll evaluate that at x equal b, x equal 1, and subtract. The arctan of 1 is pi over 4. This is a finite constant that's being subtracted away, so that's not going to bother the convergence or divergence of this limit. On the other hand, this does contain b, and we have to think very carefully about what's going on here. Let's remember what the graph of the arctangent looks like. As the input into the arctangent function becomes large, the value of the arctangent approaches pi over 2. There is no number that I can feed into the arctan function, though, that gives me exactly pi over 2. If I say arctan of infinity equals pi over 2, that doesn't make sense. What does make sense is to say that when I make the b very large, arctan of b is very close to pi over 2, so that the limit of that term is equal to pi over 2. But there is no spot on this graph that has y coordinate pi over 2. In any case, since the limit of both terms exists, the value of the integral from 1 to infinity, 1 over x squared plus 1 with respect to x, is pi over 4. The improper integral converges, and that tells me that my infinite series converges by the integral test. If I want to be all picky and official about it, I'll write a sentence that looks like this. We had already checked that the hypotheses of the integral test were satisfied, so I don't need to say that again. I'll just say, since the improper integral converges by the integral test, we know that the infinite series converges, and then put a period at the end of statement. As another example, I want to look at the sum I equal 1 to infinity 1 over I squared. The f function that I'll use is f of x equals 1 over x squared. This does have a discontinuity at x equals 0, but since we're only interested in x's that are 1 or bigger, that doesn't matter to me. On the relevant interval of x values, f is positive, continuous, and decreasing, so the hypothesis of the integral test are satisfied. Calculating the corresponding integral, it converges to 1. By the integral test, the sum I equal 1 to infinity 1 over I squared converges. I wanted to do this one separately because of something that I want to point out here. Because the integral worked out to be a finite real number, that tells me that the infinite series converges. But a common point of misunderstanding is that some people will think that the infinite series converges to this value 1, which is not right, and I'll show you this in a second by looking at a few of the partial sums. If I just look at the first three partial sums, the first one is 1, the second one is 1.25, the third one is 1.36, and then an infinite string of ones after that. Because the terms that I'm adding in are positive, the partial sums will continue to get bigger. There's no way that the value of the infinite series can be 1 because obviously it's at least 1.361 repeating. We have no way to see that this is true, but the sum I equal 1 to infinity 1 over I squared is pi squared over 6, which is a little bit bigger than 1.6. This is definitely not equal to 1. The fact that this integral comes up 1 is almost beside the point. All that matters is that it comes up a nice finite number. That tells me that the infinite series converges. It doesn't tell me what the infinite series converges to. The series that we were just looking at is actually a special case of a more general collection of series. Take a positive constant p and look at the sum I equal 1 to infinity 1 over I raised to the p power. The preceding example was one of these with p equal to 2. These kind of series are called p series, and they show up often enough in enough different situations to be worth being aware of. P being positive means the conditions of the integral test are satisfied. Convergence or divergence will be controlled by whether or not this improper integral converges. If you'll look back in the section on improper integrals, though, we've already figured out what happens in integrals of this type when p is a positive constant. For positive constant p-values, this integral converges if p is bigger than 1 and diverges if 0 is less than p is less than or equal to 1. Because of this fact, we already know all about the p-series. For constant positive p, we will get convergence if p is bigger than 1 and 0 less than p less than or equal to 1 will give us divergence. With that in mind, certain questions are now very easy to answer. This series converges because it is a p-series with p equal 3, and 3 is bigger than 1. This series diverges. It's a p-series, but p is 0.99, which is less than 1. This series converges. It's a p-series with p equal to pi. Pi, being about 3.14, is bigger than 1. This is 1 over square root of I. That's 1 over I raised to the 1/2 power. This infinite series diverges because it's a p-series with p equal to 1/2, which is less than 1. This is about all I want to say about the integral test. It's sometimes useful in deciding whether a given series converges or diverges. I hope everybody's having a good day. I'll talk to you again soon.